I would like to explain to you the common base amplifier. I don't think that my previous explanation of the common base amplifier is good. So I want to make the other recording and explain it later. And this is the small signal model that is used. This use hybrid model, and this use T model. And in this explanation, I would like to use T model instead of the hybrid model. The difference is only the base resistor, R pi, R is placed here or placed here. Since we are going to use T model, so if we place the resistor here, then the RE is around 25 millivolts divided by IE. Okay, let's remember that. And this is a very small one, small resistors. And let's use this one as our model. And I redraw it to the other, I redraw it to my handwriting notes. Okay, let's remember this is our equivalent model. For the common base, okay, we are going to have a circuit something like this. Okay, this is our RC. Okay, we will have let me see what kind of resistor transistor is a PNP transistor. This is a PNP transistor. It doesn't matter, but let me have it more consistently. And in order that the transistor to operate, we are going to have this B, this E, and we have this voltage, VB, which will be greater than 0.7 volts. Okay, and then we are going to have another volt VCC here. And usually we will place our input here. This is our input and to the ground. So we can redraw the small signal model using T model. If we use T model, then this is the base, okay? Let me redraw it. This is the base. Base is here. And we have RE here. And we have a current. We have a current here. Flow through here. Which are alpha IE. And we have the RE here, the big RE here. And this is the ground. And this is the input. And because that in a small signal model, the base is connected to ground now. And this is, there are a RC resistor here. And the RC resistor also connected to ground. And when you say these two connected ground, actually this part will be connected to here. Okay, let me redraw it so that we can make it clearer, okay, so that you can see better, okay. So we have, in a more traditional way, we have this one, we have V in of T, and V in of T connected to a resistor to ground. And we connect the other resistor See this one here, to ground too. We have RE here. And then we have a current. We have a current source. This is a control. Control source here, but this control source, as you can see, is connected to here, and is connected to the ground. So this is our current source, which is alpha IE, and then it connected to a resistor here, RC, is also connected to ground. So if we can have this one. So this one makes things very easy, because that we can easily calculate the IE. The IE is equal to the V input divided by the RE in parallel with RE. Okay. But this will be our output here. This is with our output here, and this is ground. Okay, so we have this one, this output of T, but the output of T is equal to IC multiplied by the RC here. But what is IC? Is alpha IE multiplied by the RC. But what is IE? It's equal to alpha V in divided by RE in parallel with RE and RC. So if we move around, we have V output of T divided by V input of T. This V input of T will be equal to alpha RC RE in parallel with RE. But if beta is much greater than 0, then alpha will be close to 1. So the voltage gain will be equal to V out of T, V in of T, which will be equal to RC over RE in parallel with RE. Okay. So since RE is 26 millivolts divided by RE, so if IE is large, then RE is small. Then the gain will be equal to RC around RC over RE. Okay, because a big resistor in parallel with a big one, in parallel with a small one, will be approximately equal to small one. Okay, but however, if IE is small, then RE is no longer small. Then the gain will be returned to RC, where RE in parallel with RE, small RE. So for example, if IE is equal to 10 milliamp, then RE will be equal to 25 millivolts divided by 10 milliamp, which will be 2.5 ohm. So if IE is small, then RE is small, then RE in parallel with RE will be something that we can calculate, which is RE multiplied by the RE, which is RE plus RE here. Okay. So therefore, if IE is even smaller, for example, 1 milliamp, and this one will become 25 ohm. Okay. So let's go back to see the simulation I have made before. This is the common base circuit, which is quite standard. You will see that here we have 1000. There's 1000. So if you see, if the gain is equal to RC and the RE, then the gain should be equal to 1. But the real case is not, because the gain should be equal to RC and RE in parallel with RE. And since you can calculate that this one, for example, this one is 3 volt. We have 3 volts here. Since we have 3 volt here and minus 0.7 volt, which is the BE junction threshold voltage, and divide by 1000. Okay, and this one will become 2.3, which will be around 2.3 milliamp. Okay, so the RE will be 25 millivolt divided by 2.3 milliamp, which is around 10 ohm, right? 9 to 10 ohms here. But 10 ohm in parallel with 1000 will be equal to around also 10 ohm. So the gain will be equal to 1000 divided by 10, which will be 100. Okay, so it's quite big, but in our simulations, let's see, the input is 0.1 volt. Okay, and this one, the output is from here to here, so you can see it's around 8.8 minus 6.4, which will be around 2.4 volts. And 2.4 volts divided by 2 will be 1.2 volts. 1.2 volts is around from here to here, 1.2 volts. And 1.2 divided by 0.1 is 12. So the gain is 12, not 24, it's 12. So that means, although the calculation is 100, but basically it cannot go that big. It's only 12. That means that in our calculation, okay, although we can see that the gain may be 100, but in the simulator, of course, simulator is closer to the real things, and now it's only 12. That's why I want to tell you that although it can calculate, but sometimes it just cannot be very close to the idea you want. You have to go through the simulators. But to understand the basic theory is very important, because that you know which kind of amplifier you want to use. But only when you put the real resistor value and the real transistor here, then you know how many times you can amplify signals. Okay. All right. Thank you.